Mr. B here. This is Lesson 2-5, Testing Equivalence. The assignment is, as usual, do the CTI and the AM. Take notes about this, and when you're done with that, check your work, bring it over, get onto your mastery quiz. It'd be great. There's some mental math here that asks you to estimate to the nearest integer these various terms to the side. You should be able to kind of glance at that, see what you come up with just kind of in your head, and then compare it to what you get when you calculate it. See how you do. In this lesson, this idea of equivalence is pretty powerful in algebra. We use it a lot when we're comparing things, when we're working with equations. If we can find things that are equivalent or equal, we can use that property. So equivalence is something you'll want to know about and want to be able to understand. An example of equivalence is this toothpick problem. We can see they're talking about Yolanda and Suki. They came up with different patterns. The question is are they equivalent? Let's go into the next page. We've got an example, and I'll come back to this one after reviewing just the whole lesson, and we'll go through this one a little bit more carefully. But in the example, it uses different methods to test equivalence. Now, what's hard sometimes is if two expressions are equivalent, you have to do a lot to make sure that's really true for all values. When they aren't equivalent, all you have to do is show that one time, and then you can say they're not equivalent. So in fact, proving it to be not equivalent is actually easier than the other way. In guided example 2, we'll come to that. We'll talk about something that has that property to it. Example 3 gives us another method of showing it, and then it's asking for a counterexample to demonstrate that indeed it is not, if in fact we show that to be true. Example 4 is using properties of algebra to solve the problem. And I'll be going through an example like this when I go back through the lesson. Using properties is part of algebraic showing your work. When I ask to see your work, this is what it's going to look like. You don't have to write distributive property and combining like terms, but as you use a property, I'd like to see how that impacts your work. And we go step by step in a column format. Try to line up the equal signs as best you can. It doesn't have to be exact. And get them down to where you can finally reach a conclusion about whether they are equivalent or not. That's 2-5. I'm going to get going on the examples. Pay attention to them. Make some notes. Make sure you got this in your notes so you can refer back to it. You also have the examples in the book that you can go through that are written up. If you have questions, put them on the board, ask them, request a mini lecture, whatever it is it takes to get the information you need. Okay, let's go through some examples here for 2-5. Here's an extra example number 1, and it's asking you to test whether 3x, open parentheses, times x plus 2, close parentheses, plus 5x, and x times 3x minus 1, that's all in parentheses, plus 12x. You want to test whether those are equivalent. I'm going to go through 3 methods here for how you could do this. The first method is using numbers to test for equivalence. Just want to verify that, are these the same things through just some testing. Now, there's an infinite number of numbers, so if you wanted to check all of them, that would be a lot of testing. But we can check a few just to see. So here's our equation. So first thing we're going to do is we're going to say that x equals 1. And if that's true for our first equation, that's we'll call this one 1, and we'll call this one 2. So for 1, we get 3 times 1 times 1 plus 2 plus 5 times 1. Break this down. I got to add those together. Order of operations, that's in parentheses. We do that first. That's 3. 1 plus 2 is 3. 3 times 1 is 3. 3 times 3 is 9. right? 1 plus 2 is 3, and I'm going to multiply what's in here times this 3 plus 1 term. 3 times 3, 3 times 1. 3 times 3 is 9. 5 times 1 is 5. 9 plus 5 equals 14. That's equation 1. Let's look at equation 2. That's going to be 1 times 3 times 1 minus 1 plus 12 times 1. Do this first. 3 times 1 is 3, minus 1 is 2. 1 times 2 is 2, plus 12 times 1 is 12, plus 12. 2 plus 12 equals 14. So I've got my first state of equivalence for 1. Well, that's only one number, and it may be that's the only number that they're equal. So I need to check some other numbers to see what's going to be equal to this or not. So let's take a look at another number here to see how that's going to work out. Okay, we'll take a look at this with another number. So what was our equation again? I got a new page. I want to just verify that was x times 3x minus 1 plus 12x. That was our first equation, and our second equation was 3x times x Nope, I got those backwards. Okay, let's try another number. I've moved to a different page, and here I want to make sure I get my equations right. So for 1, I had 3x times x plus 2, and that was plus 5x. And our second one was x times 3x minus 1, close the parentheses, plus 12x. Now I'm going on to a different page. I want to make sure I get this right. This is a pretty common place for a mistake to be made, where you're moving along, you're writing an equation or expression down for a second or third or fourth time, and you do it wrong. You want to go back and check. Don't just assume that because you wrote it, it's going to be right, because you could do an awful lot of work and end up with a wrong result. So let me just check this. You could check it too, and yep, looks good. So let's go ahead. The first one we did was x equals 1. So now let's try a different number and see whether it's going to work. And it doesn't have to be really difficult when we do these things. We can choose numbers that are fairly simple. Choosing 1 or 0 has some risks, because 1 and 0 have identity properties that might give you some strange results. So I'm going to try x equals 10 because I know multiplying by 10 is pretty easy. So I'll try doing that. So for equation 1, I get 3 times 10, well that's 30, times x plus 2, that would be 10 plus 2. 10 plus 2 is 12, plus 5 times 10 is 50. So you've seen I've gone ahead here and I've done the multiplication, I've taken care of the addition, I've done some more addition here. So I've got these done in these equations, and now I can go back through and try to see about what am I going to get when I put all these things together. So let's see, 30 times 12, okay, 30 times 12, that's going to give us, let's see, 360 plus 50, and if I add those together, that's looking like 410. Let's look at 2. We've got 10 times 30 minus 1 is 29, plus 12 times 10. 12 times 10 is 120. 29 times 10 is 290, plus 120, that's going to equal 410. So now we've got 2 examples that we've gone through where we have compared the expressions by substituting values into the expression. It's just 2 values. It may be true. We could say it's true for 1 and 10. We might be able to make a case for others in between. But another method that would allow us to look at a lot more expressions or a lot more results is by using your graphing calculator. And in your graphing calculator, we'll be able to compare the expressions and look at a table of results and just scan on through it and through it and through it and see if it's true. And again, it's a finite number of results. We can only say it's absolutely true for those things we've compared, but it does give us some chance to say it's likely that these expressions are the same. In this case, even with the 2, I think we would say it's likely they're the same. So for our next part of this example, the next method will be to use the graphing calculator. So get that out and work along with me as I go through the process to solve that. Okay, we're carrying on with the first example, extra example for 2-5. In the example in the book for their example 1, the next thing they go to is to use a table to test equivalence, and then they go to use a graph to testing equivalence. I'm going to flip that. I think it'll be obvious to you, but when I come to a point where it's easy to explain, I'll go ahead and do that. So we're going to select graphs. We got our graph going. We have our entry bar for our function. It might be on top, it might be on the bottom in your calculator. We're going to carry on with the same equation, or expressions we've been using. So that was 3 times x, 3 times x, and then open parentheses, x plus 2, close parentheses, and that's all plus 5 times x. So that's our first expression. We hit enter, and it doesn't like, oh, I see, I made a mistake. Where I did it was right up here, 3 times x, and x times the stuff in parentheses. I needed to put a multiplication symbol in there. So now I've got that, and let's hit enter, see if that, yeah, there we go. So now we got a graph. It's a little bit off scale, but I'll live with that. I'm going to point at the graph. I'm going to double click, and now I have another entry bar. So I can put in an f sub 2, f sub 2 of x, the next expression. And that one was x times, open parentheses, 3 times x minus 1, close parentheses, and then that's plus 12 times x. And I'm going to hit enter. Okay, and now I have 2 graphs, and it's really inconveniently put both expressions on top of each other. So I'm going to get my hand, I'm going to grab one of them and move it down so I can see the 2 of them without having to move stuff around. Now it's a good time to kind of change our window, and I'll go in here to the axes. I'm going to grab it and I'm moving it up, and you can see what's happening is it's changing the window. I could go into the menu and do the whole window thing, but this is pretty easy, kind of gets me what I want. I probably want to bring this in a little bit from the X side. it to go out a little bit. I think I want it to go out. Okay, enough playing with the window. The two expressions are there. I've got my F1 and F2, and they appear to be coincident. I could try to zoom in on this a bit, but it looks like they're right on top of each other. So that's good. So this is the graphical method. I've graphed it. The correct response to this would be they appear to be equivalent. I haven't looked at the infinite number of values available, so I can't know for certain, but I'm pretty confident. Now we could go from here to a table, and this is why I chose to do the graph first, is I've got the expressions entered in as functions. I've graphed it. Now I go to Menu, to Table, and Split Screen Table. And this gives us our next method, which is comparing results in the table. And I can see as I go through it, I have my F1 here in the first column, F sub 2 in the second column. And I have values that, as I scroll through it, appear to be the same thing, and I find no differences in there. Point with all this is make the graphs first, and then you can just go to a table. If you have the expressions, it's pretty easy. Put them in. You got a table available to you with the graph. Nice way to compare the two. So we've now covered 3 different techniques. The first technique was substituting values and comparing. The second technique was making a graph and seeing how the graphs look. And the third technique was to make a table of data from the expressions and compare the table for those two expressions and see if they appear to be equivalent. What we can't know from this is, are they always equivalent for any number, anytime, anywhere? Because we don't have enough time to look at an infinite number of values. So to find out if it's equivalent and will always be equivalent, that'll take us into our next method, which is to use properties to test for equivalence. Okay, Mr. B, this is a 2-5 extra example 1. This is the 4th method in the series. We're going to take a look at these two expressions and see if they are equivalent. And in this case, we're going to show that they are equivalent always, or not equivalent always. And we'll see how that will work out by using the properties that we've learned in algebra. So the first one we're going to look at is the top one, the 3x times, in parentheses, x plus 2, close parentheses, plus 5x. So here's that expression again. That was 3x times x plus 2 plus 5x. So what I want to do with this is I'm going to use the distributive property first. So 3x times x plus 2, that'd give me 3x squared, plus 3x times 2 would be 6x, plus 5x. And this was the distributive property. And it's the distributive property of multiplication over addition or subtraction. In this case, it's addition. We combine like terms next, and so 3x squared, just one of those, and then I've got 6x plus 5 more x's would be 11x, and that's combining like terms. And remember, the square on this, the exponent, makes it different. It's x times x versus just x. And so I've got that this is 3x squared plus 11x. Let's take a look at the next one, see what we get to. And in that one we had x times 3x minus 1 plus 12x. So again, we'll use the distributive property. I'm going to put in an abbreviation, distprop, and I'm going to use x times 3x is 3x squared. X times a negative 1 would be negative x. I'm going to change this into addition using the algebraic definition of subtraction, in that 3x squared minus x is the same as 3x squared plus the opposite of x. Then I still have this plus 12x. I'm going to combine terms. And 3x squared, that's the only one with a squared to it, so 3x squared plus 12x plus a negative, plus the opposite of x would be 11x, so plus 11x. And what I see here is that for these two, that in fact I have the same thing, that the 3x squared, 11x, 11x. And in doing this, I've been able to show that our original equations that we had here, in fact, can be manipulated using algebra and show that they are in fact the same expression. And in this case, we've shown that they are always the same expression. So this is the fourth method. I've got a couple of additional examples to go through that might be of interest to you, so if you need some help with it, do take a look. And I'll see you on the next example. Okay, Mr. B, 2-5, this is the extra example 2. This is similar to the guided example 2 that is in the textbook. I'm just taking a look at a different expression and comparing them. So we're going to show that these two expressions are not equivalent. There's some methods to it. What's nice about showing that they're not equivalent is we really only have to do that once. If we can show that they don't equal each other one time, then we're done. So our first method with this would be to take the 7x minus x and 7, and we're going to try to show by substitution that these don't work. So that's going to be our first technique, would be one, substitution. And we're going to just pick a number. So what do you think? Pick a number between 1 and 10. How about 3? So we'll go x equals 3, and we're going to substitute that in for this one. We already know there's no x's, so this first one, or the second one here, that's just going to be 7. In this, we're going to get 7 times 3 minus 3. Order of operations, we do the multiplication first. That's equal to 21 minus 3. And 21 minus 3 is equal to 18, and we know for pretty sure that 18 does not equal 7. So this is the first method, substitution. Real quick, we plug something in. We found out that indeed 7x minus x and 7 are not equivalent expressions. So that's our first technique. Our second technique is to look at it as a graph and a table. Now, we went through this method in the previous example where you create two functions, one that's 7x minus x and 7, and you plug those in and you compare them to see if indeed they're the same. Or we could just very quickly graph this one by hand and show that it would always be the case. So let me put in a couple of lines and use that to build a quick graph. I'm doing this one by hand. So this is going to be x. Here's y. We've got the some tick marks we can kind of mark in here. You know, didn't I mention I want you to use graph paper? And here, what am I doing? Just putting it up by hand. So that's one, that's one. We know that the 7x minus x, we can put in a few values for that. We'll make a little quick table. So I've got x, and it's going to equal y, or f of x if we were. So fx is 0. If x is 0, then y is 0. 7 times, so 0, 0. That's good. And let's pick something else. We'll make it, again, I want to try to keep it fairly simple. If x is 1, 7 times 1 is 7, minus 1 is 6. And so I've got the point at 1, 6. Boy, that y is inconvenient, isn't it? Get rid of that. This is 1, 2, 3, 4, 5, 6, 7. So 1, 6 is a point. 0, 0 is a point. And we're going to have a line that's going to go down between these two. And just kind of continue on forever, actually, in both directions. If you're doing this on your graphing calculator, it's going to just show it going off the edge of your window. And then what's going to happen with this? This is just 7. Well, this is a case where we would say that there is no x. X could be anything, because this is like an equation that's 7 plus 0 times x. And 0 times anything would be still just 0. And so we're saying that this whole thing was going to be our y. So it doesn't really matter what x is. If x is 1, y is 7. If x is 2, y is 7. And in fact, this is equivalent to 7 equals y. And in that case, since it's always going to be true that y is 7, we're going to have a horizontal line that's going to be going out here in both directions. This line is going to go forever. And no matter what x is, the result will always be 7. Now here in this graph, we clearly see that there's only one solution for which this is true, that 7 and 7x minus x are equivalent. There's just at that one point of intersection. For many other values, they have no equivalency. So this is our second technique. We showed by graphing that it's true that they are not the same. Our third technique, and this is something you could do with your calculator, is to build a table. From that table, show that indeed they are not equivalent. We can do that by hand real quickly. And again, for expressions that are not the same, it's often easy to do because we just have to show once that they're not equivalent expressions. So let's look at the next one, which would be our table. And we kind of started some tables already when we were in on this this graph. So that we had 7x minus x, and we're going to change that into an equation. 7x minus x equals y. And this one, the next one, is the same as, And we're going to make that a y sub 1, just so we're not confused. And this is 7 equals, and we'll make that a y sub 2. And so now we just want to put in some values of x. Well, so this is y sub 1, y sub 2, and x. So if x is 0, then we concluded that the y sub 1 would be 0, and y sub 2 is going to be 7. Hey, what about negative numbers? We didn't look before. So if it's a negative 1, so if that's going to be true, a negative 1 times 7 minus a negative 1 would be plus 1. Minus a minus is a plus, so it's going to be negative 6, and y sub 2 will be 7. And we had our 1, that was a 6, and that was 7. Now we could keep going with this, but already we see that in fact these are not equivalent expressions. So 3 methods. We compared them by substitution, showed that it wasn't equivalent. We graphed it. We show they're different graphs. They're not equivalent. Last technique is we made a table. We have elements in the table, and we see that for a given x, the y value is different. Therefore, they are not equivalent. We only have to show this one time. We're on to another example for 2-5. I mentioned earlier that if you have a counterexample to show that two expressions are not equivalent, it's sufficient to just do that one time. One counterexample is enough to say that the expressions are not equivalent. It's more difficult when they are equivalent, because if we just cite instances, that doesn't cover everything. And so to show that it's always equivalent, we use algebraic properties. So I want to go through that procedure again with these right here to show that these two expressions are in fact equivalent. Equivalent means equal. So I could go in here, and I may be going to erase some of this line here. Go. And what could be put in here is, in fact, an equal sign to show that these two equal each other. But I'm going to go through this. I'm going to take one at a time, and we'll see what it comes out to be. So I'm going to put that one away for a second, come back in here, and we're going to go ahead and simplify this expression. We start with the distributive property. So 5 times 3a squared is going to be 15a squared, minus 2 times 5 is minus 10a, plus 6a, and 6 times a negative 3 would be minus 18. I'm going to combine like terms. I have a 15a squared, negative 10a plus 6a is going to be minus 4a. I'm going to make this plus a negative 10, so I can come back to plus a negative 10 minus 6 is 4, plus a negative 4a minus 18. I think I'm as simplified as I can get. No more like terms, I'm done. So let's see what happens with the other expression. We'll go ahead and get this one out of the way for a second. Bring our other expression back. And we'll go ahead and we'll use the distributive property on this one. 2 times a is 2a, minus 2 times 9 is 18. I'm going to go ahead and change that to plus a negative 18. And plus 3a times 5a is 15a squared. 3a times a negative 2 would be minus 6a. Now I'm going to change this to addition, so plus a negative 6a, algebraic definition of subtraction. And so I'm going to combine like terms. I've got the 2a and plus a negative 6a is the same. Got an 18 and a 15a squared. I'm done. I'm going to start with the expression with the highest exponential value. So that's 15a squared plus the next lowest with a variable. So 2a plus a negative 6a would be minus 4a and plus the opposite of 18. So let's see how we do here. And again, we see that these two terms are equivalent. I'm going to erase this line so that I can go back in and say that these are equal expressions. Equivalence means equality. When you're asked to show equivalence, you're being asked to show that indeed they are equal to each other. We have these two. They show that they are the same expression. We have shown they are equivalent. That's the end of 2-5. If you have questions, please bring them to class. Write them on the board. Make sure to take good notes so that you can share those with me. And good luck on the work, and best of luck on the mastery quiz.